thanks Math Department at UNT for inviting me to do this colloquium. And thanks to all of you for coming to hear about congruent numbers, which is really the subject of this talk. And I hope you're very attentive. You may have noticed already the title on the slide is slightly different from the title on the poster. Just want to keep everybody on their toes. And what I do when I lecture, when I give classes at Berkeley, is I try to lecture with my iPad and write on the slides. That seems to be a very good technique, which I never did before COVID. And I'm writing the words congruent numbers, which I already said. And that's really the underlying subject of this talk. And you can find other articles and talks on YouTube about congruent numbers. But the approach I'm presenting is slightly different because I want to talk first about Fibonacci. So if you ask a math student about Fibonacci, they probably know about the Fibonacci numbers. It's a sequence where every number is the sum of the previous two numbers. And there's even a good number file video about Fibonacci numbers. The sequence typically now in computer science books starts with the 0th term 0, and then the next two terms are 1. And if you add 1 and 1, you get 2. If you add 34 and 55, you get 89. If you add 89 and 144, you get 233. And the numbers increase exponentially, actually. The base of the exponent is 1.62 or something. And if you take a discrete mathematics course, you learn about these numbers, and your teaching assistant might give you examples of how these numbers occur in nature. You know, the number of petals of flowers tend to be a Fibonacci number. And there's a good example in nature in Berkeley. There's a Fibonacci car, a Nissan Leaf, with a license plate 2358, and I see it quite often north of the university, and I've never stopped the owner to ask what the owner does. Is he only in mathematics or not? But it's really a great thing that I show students when I lecture on Fibonacci numbers. And then these numbers occurred again in an article about 15 months ago, I think it was, in the New York Times, where you can see the 011 in the foreground and 235 and so on. And this was an article about something called the Online Encyclopedia of Integer Sequences, which is a website that was celebrating its anniversary at the time, I think, in fact, its 50th anniversary. And the idea is oeis.org. If you get a copy of these slides from me, which you can get by sending me email, the red text, everything in the red text, most of it anyway, is a link. And you can, mouse down on Online Encyclopedia of Integer Sequences, and you get to oeis.org. And the value of this website is that if you have a bunch of numbers that you're computing, and you want to know what family they belong to, you can type in the first few numbers to oeis.org, and it'll come back and tell you what sequences, if any, match the numbers you found. And the most common thing, if you're doing some computation, is you will get a single sequence, and then you realize that you have some mathematical structure that reflects the sequence, and you go in and you try to find out why. So it's a fantastic tool for computation. And when I was a student, and even much beyond that, I kind of thought about the names of our mathematical ancestors: Gauss, Euclid, Euler, Fermat. So I listed some of them here. And the basic thing is that I had only the vaguest idea of who they actually were as people and when they lived. Although, I have read, for example, Gauss is famous for the book in elementary number theory that he wrote, which is the Disposiciones Arithmeticae. And I've looked at that book, which is nearly identical to textbooks in number theory courses at modern universities, but I kind of couldn't very well place all of these people in time. So some of them were obviously very old, like Archimedes and Euclid. But you know, did the genre live before Newton? I have no idea. We put these people in order, and especially I had no inkling as to the time in which Fibonacci lived. Just knew the name, and it turned out that I found out that he lived in an era which is called the High Middle Ages. So you might know Monty Python and the Holy Grail. The movie takes place in the Middle Ages, so things were pretty dire at the time. Well, this is a couple of centuries after that, but not very many. So life was very hard. Children had to start working when they were around 12. And on these slides, I talk about the composers at the time of some of the mathematicians on the previous slide. Now you think of like Bach or Beethoven, and the only composer I could find around the time of Fibonacci was a troubadour named Nicoletto da Torino, whose webpage is quite funny. It says that he traveled to Burgundy and found the people annoying and came back to Italy. So this was really a long time ago, and Fibonacci lived primarily in the 13th century. He was born toward the end of the 12th century, and the thing that's remarkable is he actually published a book in 1225 called the Book of Squares. And what are the squares? Well, the squares are just the squares of the positive integers. Like 1 squared is 1, and 2 squared is 4, and 3 squared is 9, and 4 squared is 16, and so on. Fibonacci studied these numbers and the interrelation among them. We might say in modern mathematics that's not a promising topic, but at the time very little was known, and there was no kind of algebraic notation. If you talked about these numbers, you had to kind of talk in very floral language in Latin, of course. You know, we talk, add the previous number to the sum of the first two, and you take the square root. I don't even know what they called square roots at the time. There's a modern translation, which I got out of the library, by a man named Sigler, and Sigler has a little appendix at the end of every chapter explaining what Fibonacci was actually doing in the chapter in question. Because the whole thing is a very flowery language, even in English. So here are the squares, and if you think about perfect squares, you know, what are you going to do with them? Well, one thing that everyone has studied is the Pythagorean theorem, and you learn, for example, 3 squared plus 4 squared is 5 squared, and you learn that 5 squared plus 12 squared is 13 squared. So these are pretty familiar relationships. And Fibonacci did something slightly different. He took the squares and he asked himself whether 3 of them, not all the same number, could form an arithmetic progression. So an example of an arithmetic progression among squares is 1, 25, and 49. 1 squared, 5 squared, and 7 squared. And what this means is that 25 minus 1, which is 24, is the same as 49 minus 25, which is also 24. Another thing you can say is that 25 is the average of 1 and 49. It's the same statement. 1 plus 49 is 50, which is twice 25. Another arithmetic progression, if I'm not mistaken, is you can have 7 squared and 13 squared and 17 squared. And for example, 7 squared is 49, 13 squared is 169, and the difference between these two is 120. And if you take 17 squared, it's 120 more than 169, so it's 289. So that's another arithmetic progression involving perfect squares. And Fibonacci was very interested in these numbers, and he was quite interested in the differences between pairs of numbers. So here the difference is 24, and the difference here, as I said, is 120. He was very interested in those numbers and wanted to know what you could get. So if we go to the next slide, and I have blank slides in case I want to write a lot. They're all around in this sequence. And in my office before, I wrote the 7 squared, 13 squared, 17 squared at the bottom of this slide also. So now on the screen, you'll find 4 arithmetic progressions of perfect squares, 3 of them neatly typeset, and one of them just written in my somewhat indecipherable scroll. And we're focusing on the differences, which are 224 at the top, 120 at the bottom, and the intermediate ones are 720, and it looks like 100,800. So these differences, if you take large squares, as we're already doing in the third line, can be pretty big. And Fibonacci, who was writing in Latin, referred to each such difference as a congruum, or the plural is the differences are congrua. That's my Latin. And in modern parlance, we talk about them as congruent numbers. But now I want to explain, I can go to this blank slide and try that. So if we take kind of, let's do 1 squared, 5 squared, and 7 squared, that will give us the congruum 49 minus 24 minus 1, sorry, 25 minus 1, which is 24. But we can also take the 1 squared and we can multiply it by, 42. 42 squared and 42 times 5 squared and 42 times 7 squared. And then the congruum would be multiplied, all these numbers are multiplied by 42 squared, so the congruum would get multiplied in that case. Here it was 120, here it was originally 24. We could multiply that 24 by 42 squared. So we can inflate these numbers by perfect squares and get other congruent. Now I want to do something a little bit different, kind of back formation, I call it. What we'll do is we'll take 1/2 squared and 5/2 squared and 7/2 squared. So these are perfect squares in arithmetic regression, but now we've introduced denominators, so we're going to use fractions instead of whole numbers. But now the congruum 24 gets multiplied by 1/2 squared, which is to say it gets divided by 4, and you're left with 6 as the congruum when you allow denominators. And the point to me is that the 24 is a product of a square and a number which happens to be 6 in this example, where you can no longer take out the square. So the 6 is the square-free part of 24. And what I would like to do is allow denominators, if necessary, so that we can strip out the square parts of congrua in the same way that we can take congrua and multiply them by additional squares. So we have some flexibility. A congruum is a number that can be multiplied or divided by a square, and why not divide by squares so that we get only the square-free part? And here we have some examples of congrua, which you've already seen, I guess. But the point is that what we're going to do is we're going to take each of these differences, 24, 720, and 100,800, and multiply out the numbers so that you see a square and a square-free factor. And the square-free factors in these three examples are 5, 6, and 7. And you might remember the one with 13 squared and 17 squared, where the congruum was 120. You can strip out a 4 and you'd be left with 30 as the square-free factor. And so the whole business is that this talk is really about those square-free numbers that can be obtained by this process, the congruum. And we see that 5, 6, and 7 are such numbers, but we could ask, what about some other numbers? So if I go to the next slide, you see only things that I've already mentioned. So I do this a lot when I lecture, because I think my students can't really read my handwriting very well. So I write something for them, and then I flip to a slide, and the thing is typeset, so they can see it the second time. So 5, 6, and 7 are congruent numbers, and you can ask, what about other numbers? So if I take the square-free numbers, if I take the numbers less than 10, we're only talking about non-zero numbers, so it'd be 1, 2, 3, 4, 5, 6, 7, 8, 9. But among them, there are some numbers that are not square-free. For example, 4 is not square-free, it's actually a square. And 8 is not square-free, it's a square times 2. And 9 is not square-free, it's a square times 1. So if you want the square-free numbers, you can throw out 4, 8, and 9, and there are only 6 numbers left, 1, 2, 3, and 5, 6, 7. And the 5, 6, and 7, as we've already seen a couple of times, are indeed congruent. And the question is, what about 1, 2, and 3? Can we make up 3 perfect squares so that the difference between the second and the first, and also between the third and the second, would be the same number, and that number would be a perfect square. So you strip it away and you get 1. And the answer is no, you cannot do that. So this is a theorem from the 17th century. I know when Fermat lived, because I've had to talk about Fermat's last theorem many times. Fermat proved that 1, 2, and 3 are not congruent numbers. And if we go to the next slide, there's a portrait of Fermat, which may or may not be a portrait of what he actually looked like, and restatement of the theorem and some allusion to the method that he used. So Fermat had a trick that he used in number theory called the method of infinite descent. And the way this would work is you try to show that some equation did not have a solution. And the way he would do it was to assume that it does, and said, well, if there's some solution, there's going to be a smallest solution. So let's take that smallest solution. And then Fermat would do a lot of algebra and arithmetic, and he would grind out an even smaller solution. And that would be a contradiction because he took the smallest one. But the way he said it was, well, I'll take a solution and I'll make a smaller one. And then I'll repeat the process and I'll make a smaller one. And I'll keep on going, and I can do this indefinitely. But of course, if you have whole numbers and you start with a number like 1024, you can't reduce it 1025 times and still get a positive whole number. So that's the contradiction. And if you are a math student, as I guess many of you are, we all are to some extent, you will recognize that this is really a proof by mathematical induction, but has a different word from the 17th century. It's the method of infinite descent. So Fermat did that. And now we're going to go into kind of executive session, and I'll tell you how these numbers in the examples can be constructed. So I think I wrote at the very beginning one of the slides that the Greeks were very interested in a squared plus b squared equals c squared. We are anyway. I said 3 squared plus 4 squared equals 5 squared. And they knew how to generate all the solutions to that equation by some algebraic formula. And if you take these examples and you manipulate them in the right way, you will get some of the examples that we've already seen. So for example, if we do the 3, 4, 5, it's actually typeset above where I'm going to write. The 5 will stand in the middle, and the 3 plus 4, which is 7, will be at the right, and the 4 minus 3 will be at the left. And so you get the numbers 1, 5, and 7 that started the discussion. And in the same way, if you have 5, 12, and 13, you put 13 in the middle, 5 plus 12 is 17, and 12 minus 5 is 7. You get 7, 13, 17, which is this other triple that I calculated with on a few slides ago. And for this kind of algebraic reason, there is a perfect correspondence between congrua and numbers involved with right triangles. And in fact, here's a blank slide. So the story is that if you take a triangle, a right triangle, and you have a rational number as on one leg and a rational number on the other, it may or may not happen that when you take the square root of the sum of the squares of these two rational numbers are just fractions, 3/4, you will actually get a rational number. And if you do get a rational number, then the area is the same thing as a congruent number. So that's what's going on. But what you have to do is you have to allow for fractions, even if you want the area to be 6 or 7. So the simplest example you could think of is if you have let's do 5, 12, and 13. So the area of this thing is 5 times 12 divided by 2, which is 30. And 30 is a congruent number, as we've seen. If you take the 3, 4, 5 triangle, then the area is 6, and 6 is also a congruent number, as we've seen. But if you want to exhibit triangles whose areas are 5 or 7, you will have to introduce fractions, as I think we'll see in a subsequent slide. So that was the kind of end of the digression, but it's going to come back, I think, right now. And the lemma, which is what I just told you, is that a congruent number is exactly a number that can be written as the area of a triangle with fractional sides. So for example, if you want to get 5 as the area of a right triangle, you can have the legs be 22/3 and 3/2. If you multiply those two numbers together, you get 10, but it's 1/2 AB, that's the area, so that gives you the 5. But of course, what you have to do is you have to verify that the square root of 20 over 3 squared plus 3 over 2 squared is actually a rational number. It is, it's 41 over 6. 6 is a congruent number from the 3, 4, 5 triangle, but if you want 7, then you have to have some denominators. 24 over 5, 35 over 12 are the legs, and the hypotenuse is 337 over 60. So you can find a lot of these values in the Wikipedia page for congruent numbers. But if you stick with me for the next half hour or so, you may get some sense of how you can do these calculations yourself, but you have to use cubic curves. So that's part of the thing. So now, before talking about cubic curves, we're going to kind of pretend that we're ChatGPT or something. And we might say, well, 1, 2, and 3 are not congruent numbers. 5, 6, and 7 are congruent numbers. What are the congruent numbers? But just the square free ones, to simplify things. You could ask ChatGPT, but ChatGPT would say, well, I don't really have enough training data. just given me a small number of examples. So we can go to the online encyclopedia of integer sequences and find out which numbers are congruent numbers up to 119 or so. 119 is my limit just because I want the thing to fit on the slide, but you can get a pretty long list from oeis.org. And you can ask ChatGPT what's going on here. And if ChatGPT is halfway intelligent, which of course it's not, it will certainly notice that there are runs of 3. There's like 5, 6, 7 right here. Another run of 3 is 13, 14, 15. Another run of 3 is here. Another run of 3 is here. And you can probably get the idea if you're doing generative AI that these runs of 3 have to do with division by 8. So the idea, let's see if there's a blank slide. There's a blank slide right here. If I take a number n and divide it by 8, there will be some quotient and there will be some remainder. And that means that the number is 8 times q plus the remainder. And the remainder, a priori, means before you know anything, can be any of the numbers 1, 2, 0, 1, 2, 3, 4, 5, 6, 7. There should be 8 remainders. But for example, if the remainder were 0, that would mean the thing is divisible by 8. And 8 is a multiple of 4, so the thing is not square free. And in the same way, if the remainder were 4, the number would be divisible by 4, because 8 is divisible by 4, and it would not be square free. So there are only 3 possible remainders, 1, 2, 3, and 5, 6, 7. And if you look at this table, you will see that whenever the remainder is 5, 6, or 7, the number appears on the table. And if the remainder is 1, 2, and 3, you might think it's not going to be on the table. So, for example, suppose you get beyond the single digits, and you look at 2-digit numbers. Well, an example of a number with remainder 1 on division by 8 is 9. Well, we're not going to talk about that because it's not square free. But you could have 10, which is square free, that has remainder 2, and it doesn't appear on the table. And 11 doesn't appear on the table. You have to skip to 13 because if the number were 12, it would also not be square free. But then 13, 14, 15 appear on the table. They have remainders 5, 6, and 7. And this is pretty good, and it shows you what's going on. And if you were, kind of satisfied with some small progress, you kind of walk away from the thing and say, okay, I've understood it. Remainders 5, 6, and 7 work, and remainders 1, 2, and 3 don't. However, there are some red numbers in this table where the exceptions occur. And there's the phrase, exceptions prove the rule. And I don't think these exceptions prove the rule at all. They kind of show that the rule is wrong. Although in ancient times, the word prove was actually used in that way. It kind of puts the test to the proof, sees whether or not it works. And it doesn't, because 34 has remainder 2 when you divide by 8. And 41 has remainder 1. 65 also has remainder 1. On this table, the remainder 3 doesn't occur, but okay, that's possible. The table's not very big, but it's very disturbing if you study something and you think you've understood the pattern, and then you discover some sporadic phenomenon. So that's really kind of what's going on. There's a second level explanation that needs to be provided. And also, if you're kind of on your toes, is simply of the form y squared equals x cubed minus n squared x, where n is a positive integer, which may or may not be a congruent number. And the reason we're looking at this elliptic curve is to see whether or not the integer is, in fact, a congruent number. And if you factor this cubic equation, you see that it has x and x minus n and x plus n as its three factors. So these are distinct factors. The roots are distinct. They're 0, n, and minus n. And if you put x to be 0, n, or minus n, then the right-hand side will be 0, and you can get a solution to this curve by taking x to be one of those three numbers and y to be 0. And the reigning question is going to be whether or not there are other solutions in whole numbers or fractions, x comma y. Excuse me. So this is a situation where if you were trying to understand this equation with a graphing calculator, you would have no problem. You would take, the x-axis, and you could think about, first of all, the cubic curve, y equals x cubed minus n squared x, and this curve would go through the x-axis 3 times, so it would look something like this. And then if you wanted to graph y squared equals the thing, you would take this kind of curve and you would just take the square root of y. It's square root of x cubed minus n squared x instead of the actual number x cubed minus n squared x. You cannot take the square root of a negative number, and so what would happen is that between minus n and 0, there would be what's called an egg. You get an expression like that. And between 0 and n, there would be nothing, and to the right of n, you would have some infinite branch like that. So this would be the graph of y squared equals x cubed minus n squared x. And it really is the sort of thing that you can produce, on a computer screen, or with a graphing calculator, with all technology, any way you like. Just get, Mathematica to graph it. But the problem is that when we are interested in the arithmetic geometry, we're just interested in those solutions that happen to be integers or rational numbers. And you can ask, are there any? Are there finitely many, infinitely many? What's going on? And if you study an elementary book on elliptic curves, like a book by Silverman and Tate, some people are studying in a reading course, you get answers to this kind of thing. The first thing I want to tell you, which is just simple high school algebra, is that a number n is a congruent number if and only if this elliptic curve has some points other than the ones on the x-axis. And the reason for that, as I alluded to, is just complete algebra. If you have a solution x comma y, then you can write down 3 squares of rational numbers where the difference between the second and the first and the difference is equal to the difference between the third and the second. And that difference is going to be some square times the number n. And the argument works both ways. So this is really just complete algebra, and it doesn't at all bring in any of the theory of elliptic curves. And in fact, this proposition, maybe I say in a later slide, was apparently due to the genre. So the ancient people from the 18th century or whatever So this is not a new observation. And you can also, maybe I should skip this slide because you don't want to see a lot of algebra, but if you have a solution x comma y with y different from 0, you can write down the expression, well, I did, it's on the center of the screen, where you have 3 sides of a right triangle, and the area of this triangle is actually n. And, okay, so let's do this. For example, if n is equal to 6, 6 is an area, as we know, in the 3, 4, 5 triangle, you can get that 3, 4, 5 triangle from the point -3, comma 9 on this elliptic curve. And you can check, you know, that if x is -3, x cubed is -27, but then you're subtracting 36 times 3 with a minus sign, so you're adding 36 times 3, and the result will be, if you do it right, 81, whose square root is the 9. So this is another way to see what I'm saying if you prefer the right triangles to the optic of Fermat from 1225. And it's good to illustrate propositions by numerical examples, which I do on this slide. So for example, 13, 14, and 15, that's a run of 3 that we saw on the table from OEIS. All 3 of those numbers are congruent numbers, and you can find out that they are congruent numbers by exhibiting solutions to the cubic equations. And in 2 of the cases, 14 and 15, you can get solutions with integer coordinates. But for 13, you have to go pretty far deep with 25 squared and 25 cubed in order to get a solution in rational numbers. And you might ask, how do I get these numbers? And the answer is that there is a lot of computer algebra software that you can get even for free that will tell you some points on an elliptic curve. And the software that I use is called SAGE, S-A-G-E, which initially stood for Software for Arithmetic Geometry Experimentation. But it's a good package, which you can get from sagemath.org, and you can download the thing for your laptop and play around with it. And there's a lot of decent documentation that you can search for online. You know, how do I find rational points on the elliptic curve using SAGE? You'll get to the description, and you can try it out for yourself, which is actually a lot of fun. But now in this proposition, we're going to get a little bit more serious and invoke some theory of elliptic curves. And the theory is, going from the second line to the third line, if you have an elliptic curve of the type that we're considering, and it has a solution aside from a solution on the x-axis, then it has infinitely many such solutions. And of course, the converse is clear. It has infinitely many, it has at least one. And you don't need a lot of the theory for an elliptic curve in order to prove this, but you have to know at least something that I hope to explain to you in the next few minutes. And before that, there's maybe a tiny moment of digression where I have a clip from the New York Times from maybe it's June 24th, 1993, where the solution to Fermat's last theorem was announced by Andrew Wiles at a conference, which I attended. And Wiles became instantly famous. And the thing that literally made the front page of the New York Times at that time. It print paper what was being used. And if you look at this thing with a magnifying glass, you'll see my name in there. And because of that, I gave a lot of lectures on Fermat's last theorem, as I said, and started talking about elliptic curves to different kinds of audiences who had been at least familiar with the concept before the proof of Fermat's last theorem. And the one thing that I want to tell you that has not been obvious up to now, but is well known to anyone who has studied elliptic curves, is that when you take the set of points on an elliptic curve, that set makes up a group. Now, there's a little bit of technicality here, which I'm not saying on the slide, but I can say it now, that there's kind of an extra point, a point at infinity that you see on the projective plane that turns out to be the best use of it. It's the 0 point in the group. But the main point is that if you have two solutions to an elliptic curve, distinct solutions to start, they will define a line. You take the line that goes between these 2 points, and you see where that line hits the cubic curve, and it's going to hit the cubic curve in 3 points, because you end up with a cubic equation that's going to have 3 roots, 2 of which are known. And if the elliptic curve has an equation where the coefficients of x and 1 are ordinary integers or even rational numbers, and if you start with rational solutions, x, y, 2 of them, then when you draw this line, you'll end up getting a third. And that's kind of very elementary fact. And the secret rule of the group law, if you want this missing point, which I'm not showing you in infinity, to be the origin, 0 point, is that when you have 3 points on a line, collinear points, their sum is defined to be 0. That's the definition of the group law. And the group that you get is very interesting in practice and in theory. And what you'll discover by example is that this curve can have only a finite number of solutions, or in another example, it can have an infinite number of solutions. And if you go to Sage, you can easily find out in practice. You input the coefficients of the curve, capital A and capital B, and you ask, does this curve have a finite number of solutions or an infinite number of solutions? In microseconds, Sage tells you the answer. But it's a slight embarrassment in the subject that the algorithm that's used has never been proved to terminate in some predictable amount of time. And so at least in theory, you could input these numbers and the algorithm would just hang and you never get a solution. So this is one of the many open problems in theory of elliptic curves. So just to give you a takeaway, even though quadratic equations were completely dominated by the Greeks, already cubic equations are hard, and they're hard in the sense that there are open problems that seem really out of reach. And one thing I want to tell you next is that if you take this group, it's an abelian group, because if you take 2 points, it doesn't matter which of the 2 points is the first one when you draw the line. And you're just interested in fractional solutions and fractional coefficients A and B. When you take this group, it has only a finite number of generators. So that's a theorem from a little over 100 years ago by Ellie J. Wardell. And what happens is if you kind of systematically ignore the points that have finite order, meaning that you add it to itself, point to itself, and keep doing that until you see what happens, you get back to 0 with a finite number of steps. If you ignore those points in a technical way, then you can ask how many points, what's the minimum number that you need to get the infinite solutions that may exist. That minimum number may be 0 if every point has finite order, but it might be 1, it might be 2, it might be 3, and so on. Although there are many people in the subject who think that the so on stops, that kind of won't go much beyond 29 or whatever the current record is. But the number of points that you need to get the infinite solutions is called a rank. And a summary of what we have so far is that if the rank is 0, then there are only a finite number of solutions. This corresponds to not being a congruent number. But if the rank is non-zero, meaning it's positive, then yes, it's a congruent number. So that was a little extra from one of the previous slides, that if you have a congruent number, there are non-zero solutions, and then there's going to be an infinite number. So the rank is positive, and if there is an infinite number, we're talking about a congruent number n. So this is a nice restatement of the fact that the congruent numbers are those for which the elliptic curve that we've been writing down has positive rank. So that's kind of very neat statement. And then you can kind of turn around and you can say, well, that's great. What do we know about ranks of elliptic curves? And the answer is, well, we actually know quite a bit, but a lot less than we'd like to know. They're kind of butt up against these open problems. So here's a blank slide. And what we can do, what has been done, is to take a kind of large sample of elliptic curves. So you take y squared equals x2 plus ax plus b. You take a and b to be small positive integers in some box. And you look at the ranks and you see what happens. Then you let the box grow in some well-controlled way. And you try to see, what's the average rank, or what ranks are occurring. And the observation, which is merely an observation, it's not a proof of any kind, is that roughly half the time the rank is 0, and roughly half the time the rank is 1, and some very tiny minority of the time the rank is bigger than 1, like in 2 or 3, and so on. And if you try to take percentages, the percentage of rank 0 is very close to 50%. The percentage of rank 0 is rank 1, it's very close to 50%. And the percentage of the ranks bigger than 1 are very close to 0%. There are these things that are just kind of, very, very sporadic. And if you try to take averages, they're just overwhelmed by the curves rank 0 and 1. And so that's a conjecture. That's a real conjecture that as you go through the family of elliptic curves, half the rank should be 0, half the rank should be 1. The average rank should be a half, average of 0 and 1. And the person who's most solely responsible for recent work in the subject is Module Bardava of Princeton, who's really revolutionized the subject. But in order to complete the story, I have to tell you that there is a conjecture that tells you about the rank. And the conjecture involves a function in the sense of calculus, like sine of x, cosine of x, or e to the x. There are a lot of x's around, so the variable is called s. And this is the L function for the elliptic curve, capital L. And I don't even remember who first used that letter L. Probably a German mathematician in the middle of the 20th century. And there's a lot of theory about this L function. And but the theory is all conjecture. So there's something called the conjecture of Birch, who was one person, and Swinnerton and Dyer, who was another, that if at the kind of special point s equal 1, which I'll try to explain in a second, the value of that function is 0, then the rank should be positive, and if the value is non-zero, then the rank should be 0. And we know a lot about this. The results were proved in the 1980s by Gross and Zagier, that did part of the picture, and Colloquium did a complementary piece. So we know, for example, that if the number is non-zero, then the rank, in fact, is 0. And on the other hand, in their work, if the number is 0, then we can't say necessarily that the rank is positive. But if it so happens that the derivative of the function is non-zero, when the number of the function is 0, that can happen, then the rank is known to be positive, in fact, it's known to be 1. So that's basically all we know about that conjecture. And I should say that when the conjecture was made, the cell function wasn't really properly defined. It was defined by a formula that only made sense for numbers s bigger than 1.5. And the fact that we can even talk about the value at 1 with a straight face is due to a theorem that was proved in the 1990s that came out of the work of Wiles and Taylor-Wiles on proving Fermat's last theorem. That work, completed by other people, tells you that every elliptic curve of the type we're considering arises from a modular form. And then this modular form has an L function, and that's the same L function that we're talking about. I guess I should admit to you that the elliptic curves that we're talking about are a lot simpler than the elliptic curves in general. And in fact, this theorem was already known before Wiles for those curves by the work of Schmor. But if you want to talk about the Birch and Swinnerton-Dyer conjecture for elliptic curves with rational coefficients, you really have to bring in Wiles and people who came after. And I'm almost out of time, but I will show a photo. So the person in the red shirt was me about 10 years ago, which in fact is very close to the time when I made my first visit to Denton. It was in 2013. So that's me here in the red shirt. And across from me, the older gentleman with glasses, that's not sunglasses, that's Brian Birch of the Birch and Swinnerton-Dyer conjecture. And I have no photo of Swinnerton-Dyer to show you, certainly none with me. But the thing I want to explain quickly, because I don't want to take too much time, is that the function has a symmetry, it's called a functional equation, where if you compare its value at 2 minus s, you get either the same as the value at s, this is for every s, or the negative of the value at s, and whether it's the number or the negative depends in a pretty simple way on the equation of the elliptic curve. And this is called sign, it's a plus sign or a minus sign. And if the sign is minus, then at s equals 1, this s here should be 1. The number is its own negative, so it has to be 0. And therefore, the rank should be positive. If the sign is plus, then if you look at the conjecture, it'll tell you that the rank is going to be, only conjecturally, the rank is going to be an even number, like 2, 0, 2, 4, 6, 8, and so on. Which means that overwhelmingly, statistically, the rank will be 0. So if you believe the conjecture, then when the sign is negative, when the sign is minus, you have positive rank. If the sign is plus, then you have even rank. And positive rank, not only positive, it's positive and odd, but takeaway is just that it's positive. And if you apply this calculus, as we'll call it, to the congruent number problem, then you'll discover that the sign depends on the remainder on division by 8. And when we see that there is a congruent number in the table, that's the case where the sign is -1, so the rank should be positive. Excuse me. But if the sign, if the remainder is 1, 2, and 3, then the sign, then the rank is 0 to 4 or so on, and it's very likely to be 0. And this actually explains what's going on in this table. I'm not going to scroll back and find the table, but if the rank is predicted to be positive, then you see the number, 13, 14, 15 in the table. And if the rank is predicted to be 0, 2, or 4, mostly it's 0, so you don't see the number in the table, but it might be 2 or 4, and then you would see the number in the table, and that's what happens. That explains this sporadic behavior. And so we expect that when n is 5, 6, or 7 mod 8, as we call it, that the rank should be positive, but there's no proof that it's positive. And when the remainder is 1, 2, or 3, then, so to speak, with probability 1, the number will not be on the table, but it might be in the table occasionally, and that's the red that you see with like 34 and 41. And here's the table again. There are 3 numbers in red, 34, 41, and 65. And for those 3 numbers, Sage Math will tell you that the rank is actually 2. And I think I explained that in the next, which is probably the final slide. So for example, 34, which is the first number, I found a whole number solution, -2, 48. You can check if that works. And so 34 is a congruent number, and this elliptic curve has positive rank, and Sage will tell you that the rank is 2. Ranks 4 and above are so rare that they only occur for elliptic curves with really large coefficients. And so if we're just looking at numbers n up to 119, you're not going to see ranks bigger than 2. So that kind of explains everything, except that it's all kind of hanging on this conjecture of Birch and Swinnerton-Dyer. And there's an abstract by a mathematician named Alexander Smith, who said that using the results that were available when he was an undergraduate, specifically he was in the class of 2016, you can prove the conjectured result for the congruent number problem for at least 41.9% of the time. And I'm sort of very interested in the fact that this article was never published. It's just on archive where people leave their preprints. And if you go to the webpage of Alexander Smith, I forget where he is now, maybe UCLA, he kind of explains somewhat sheepishly that this was his undergraduate work and he hasn't come back to it since. And he hopes to do it someday, but he's gone in different directions. So that really is the last slide, and I'll stop, and I think we're just at the right time. So that's it.
I have one very quick question.
You mentioned it wasn't proven that algorithms are terminates to the deciding that the rank was positive. Yeah. So is that is it known then that instead of congruent numbers it's 2?
I'm not an expert, but I suspect the answer is no. So when you compute a rank, what happens is you get an upper bound and a lower bound. And very quickly, as you refine the upper bound and refine the lower bound, they coincide. You know, just hang on you forever. Or maybe they will stop, but you can't predict how much time.
No other reason why it's two.
Right. As far as I know. That's a great question.
Let's save other questions for after, since it's already been by. But